So our second speaker is Parth Pathak, who's a postdoc at UC Davis, and he's going to tell us about finger writing.
Okay. My name is Parth Pathak, and I'm a postdoc at UC Davis. I'll be talking about our work on finger gesture recognition with Smartwatch, titled Finger Writing with Smartwatch, case for finger and hand gesture recognition using Smartwatch. So this work was done by graduate student Chao Su, myself, and Professor Prasad Mohapatra, all at UC Davis. Okay, so let's get started. So first of all, why we need to talk about Smartwatch? What are the things that make Smartwatch attractive? The primary thing right now is increasing popularity. If we look at the number of users, actually online users that use a smartwatch or a wristband or an activity tracker, the number is around 16%, although this number is less. Given that the technology only commercialized before like 2 to 3 years, we expect this number to be much higher in coming years. So with more newer smartwatch and fitness devices released, we'll be expecting the popularity to go further. So, and there's a difference between a smartwatch and a wristband, which I would like to clarify that there are certain devices which do not have a certain richer GUI, and they are primarily used for tracking different activities like sleep, standing, walking, pedometer kind of activities, that activity trackers. And on the other hand, the smartwatch is where you have a GUI, you can proactively either use social networks, send messages, and sometimes also use navigation. So, but the work that I present here does not make this distinction. It is, as long as there is a device on user's wrist which has an accelerometer and a gyroscope, and the work that I present is applicable. So the rise of the smartwatch itself sort of gives us a new opportunity that we now have a device which is increasingly being popular, and it's sitting on users' wrist, which gives us sort of an unprecedented access to the small-scale motion of the user's hand. We have already leveraged it for different things like activity tracking, but we can take it further. What we propose is we can actually identify arm, hand, and finger gestures when the user is wearing the smartwatch. So an arm gesture is where the gesture is primarily through the movement of the elbow joint. A hand is where the movement is primarily through the wrist joint, like turning on and turning off the volume. Similarly, if you are primarily using your fingers, in a finger gesture, you are zooming in, zooming out, that kind of a gesture. The rest of the forearm is rather not moving, and only the fingers are involved. So we'll look at all the three kinds of gestures. So if we can actually identify this kind of gestures using the smartwatch, we can actually enable applications like I can sit here and control my remote control devices surrounding me. I can control a smartphone, a TV, remotely using the gestures that I do while wearing the smartwatch. And it gives a new set of applications that we have not looked at previously. Similarly, it also poses, like the rise of smartwatch also poses a challenge, because we do not have sufficient ways of interacting with the smartwatch. The ways we know till now is touch and voice. Touch has been known to have its own limitation for a smaller screen size for a smartwatch. On the other hand, voice is predominantly used right now for the watches available, but the accuracy is still questionable. Voice recognition is still not the most user-friendly, and the energy is also another issue that is, because the microphone is constantly on, it raises another questions like that. So the one way to solve this problem would be to actually enable certain gestures which you can do while wearing a smartwatch and interact with the smartwatch itself. An example would be I can actually write with my index finger a message that I want to text to my friend, and the smartwatch actually recognizes this text message, and that enables sort of a new way of interacting with the smartwatch. So looking at this opportunity and the challenge, we will look at two questions in this paper. So first question is, can we recognize the finger gestures using the smartwatch? So the reason I focus on finger gestures is that The arm and hand gestures are likely to be, it's easier to be detected using a smartwatch because there is a lot of movement detected in the accelerometer and gyroscope in the watch when you do an arm and a hand gesture. On the other hand, when you do a finger gesture, it is not clear whether the small movement of finger is how much of that is recorded in the wrist. So that is the first question we will try to understand. The second question is if we try to write different characters using your index finger or any finger, can we recognize these characters on the smartwatch? So this is sort of a finger writing feasibility analysis that we will do. Okay. So to answer the questions, we take 4 steps. The first step is we look at, can we identify a gesture type given a gesture? So do we have, what are the characteristics based on which we can say a gesture is an arm gesture, a hand gesture, or a finger gesture? Then the second question is, if the motion energy that is detected while doing a finger gesture, is it enough to be, how much energy is recorded in the wrist? So is that energy enough to uniquely identify the gesture itself? So that is the question number 3. And then we will look at the finger writing with the smartwatch and we will characterize the performance of that. Okay, so the first question. So we use, the experiments that we do, we use a shimmer device, which is a small embedded device, which as the smartwatch. It has a 3-axis accelerometer and gyroscope. And the form factor is roughly the same size as that of a typical smartwatch. And while doing the gestures, we follow these guidelines, which is while doing the finger gestures, the forearm and the wrist is assumed to be grounded to the chair. The same way when doing the hand gestures, your forearm is grounded, but your wrist is free to move because there is wrist movement involved in a hand gesture. Similarly, arm gesture, your elbow is grounded, rest of the arm is free to move. So these are sort of guidelines, and these are also impose some limitations, which I'll discuss at the end. So using this, these are the 37 gestures we tried, and each gesture is repeated many times. So what we measure is that the energy, the motion energy that we can actually observe from the accelerometer and gyroscope in the smartwatch is a good indicator of first identifying what kind of a gesture it is. So the arm gesture will typically have more energy to it, as we can see in the figure. Compared to that, hand gesture has a comparatively lower energy. Some gestures, and finger gestures of course has the lowest energy in accelerometer and gyroscope both. What we see is also that if the arm gesture involves more rotation, like a thumbs up and a thumbs down, we see more in the gyroscope, more gyroscope energy. If it involves moving of the hand with more force, then it has more accelerometer energy. So with this simple motion energy calculation, we can identify if a gesture is a gesture type with a very high accuracy. So we apply machine learning classifiers to see what is the accuracy. If a gesture is an arm gesture or not, we can classify pretty much 100% of the time. On the other hand, finger gestures and hand gestures are where we often they're often misclassified as each other, and still the accuracy of classification is pretty high, almost 95% in almost all cases. So we know the answer to the first question, that we can identify the arm, hand, and the finger gesture given a gesture. So the second question we ask is, can we, the energy that is measured in the wrist while doing a finger gesture, is that, how much energy is measured, and is that enough for classifying the gesture, uniquely identifying that gesture? So how do we understand that? So what we do is, we actually use 3 separate shimmer devices. One sitting on the finger, which is sort of gives us the ground truth of, or the baseline data for the gesture when you are doing a finger gesture. The second is on the wrist, and the third is sitting on the forearm. The forearm case is considered because there is a commercial product available which says the forearm muscles is also a good representative of the motion involved in the arm and the hand. So with these three shimmer devices, now user carries out the finger and the hand gesture. The middle figure is the one where finger gesture is carried out, and that index finger is moved up and down with increasing frequency. So what we observed, again we compare the energy. So what we observed is the amount of energy measured in the wrist is also comparative to the actual energy in the finger, and in forearm we you observe comparatively lower energy. So wrist is indeed a good indicator of that the fingers are moving. Similarly, the same thing that we observe in the hand gesture, that is, the user opens the fist and closes it, and we observe the same thing, that the wrist is a good indicator of different activities done by the fingers. So, so this tells us that yes, there is sufficient indication in the wrist while doing a specific finger gesture, but we don't know whether this is sufficient to uniquely identify that gesture. So to identify that, we first have to understand why we even think intuitively that this will be, the movement of different fingers will be different in the wrist. So for that we have to look at the sort of the anatomy of human hand. So there are a total of 17 tendons, which are sort of the tissues which connect the muscle to the finger bones. So whenever you are carrying out a specific movement of the finger, these tissues are responsible for carrying out the movement. And the 17 tendons move differently while carrying out different movements. So with the hope that this will create a unique signature in the wrist as well, we actually look at some of the primitive gestures. So things like, okay, how can we, if we move our index finger up and down, what is the impact? So the first set of results shows that you do the same gesture, which is finger up and down, for all different 5 fingers, 4 fingers and the thumb. And the second set of figures shows that if you do different gestures with the same finger, what is the impact? What you see in the first set is that even if you're doing the same gesture on different fingers, you can still identify that. That means that the impact of doing a gesture on different fingers is also unique. So that this gives us a good visual verification. Similarly, the second figure shows that we can actually identify different gesture, different movements with even when the gesture is done with the same index finger. Okay, so this was just a visual inspection, so we have to calculate the actual statistics in order to understand or characterize the signal, the accelerometer and the gyroscope signal. So we use the activity recognition features. These features are used for walking and running detection and calculating steps. This kind of activity, these have been commonly used for in literature for the last 3-4 years. So we apply the same set of features, and the features are for motion energy, detecting how much is the energy in the motion, what is the posture of the hand, what is the shape of the curve when the signal changes, and how much is the variation over time. So we calculate all these features for both accelerometer and gyroscope, and then try to see whether which features are actually good in terms of identifying how useful they are in terms of identifying a gesture uniquely. So with the 37 gestures that we discussed before, the same gestures, and we calculate the information gain of individual features. So information gain is, again, it sort of calculates the worth of a feature, whether that feature will be useful in identifying a gesture or not. What we find is that all the features of motion energy, posture, and motion shape are actually useful. On the other hand, motion variation features are found to be pretty much not useful for gesture recognition. So, and this is expected because motion variation is mostly related to very high frequency activities, like you are running and you are trying to calculate the number of steps. So, and on the gesture, on the other hand, the gestures are likely to be sort of low frequency activity compared to running. So now let's look at the performance of the gesture recognition itself. We apply the same 3 classifiers and observe the performance. With the features that we use, the accuracy was observed to be 95 to 98% of the time. You can actually identify the 37 gestures that we used. Similarly, we see that the arm gestures are often misclassified between the other, misclassified among themselves, while the finger and the hand gestures are often misclassified between themselves. Okay, so let's quickly look at the finger writing part, which is we apply the same set of features to write different characters on the surface, and apply the same set of features and the same set of machine learning classifiers to identify whether we can uniquely identify these characters or not. And again, the accuracy is lower than the gesture recognition, The accuracy that we observe is 88 to 94%, and the characters that are often misclassified are D and U and A and R, which is likely to be compared to the shape of the characters. So. So with this, I would like to discuss the challenges or the things that we could not do well, and the limitations that we would like to identify. The thing is, first of all, the movement that we considered in this was an unconstrained. It was a constrained movement. That you are putting the arm on the finger on the chair arm, so your arm is not actually moving in an unconstrained fashion. So when we have to apply. You have to use this system in an actual practical scenario. You have to cancel the noise of the arm. Similarly, we have to understand user-specific traits, that every user does it the same gesture differently. So how do we learn and train the models like that? And again, we haven't looked at the computational memory and energy requirements of any of the schemes or the machine learning models that we propose. And these are the things that we should improve in order to actually this to be useful. Okay, so with this I'll conclude. So finger gesture recognition is feasible with smartwatch. A lot of research is needed in order to understand the unconstrained movement and resource utilization. And comparatively lower accuracy is observed for the finger writing part, and it has to be a very highly accurate system in order to for the inputting the text finger writing part to be actually practically useful. So yeah, thanks for listening. I'll take it.